Hey, it's Dr. Asatar Bear, and this lecture is on expected value. Expected value. All right, so recall that in our discussion of utility theory, we have the finding that individuals do this, right? They maximize utility, and that is always subject to, subject to their constraints, whatever they are. All right, so now the question that arises with this is what if there is some aspect of uncertainty to the decision making process? Not to the process exactly, but to the gain, right? To the cost or the gain, uh, because we're saying, all right, look, to do one more of something, right, what is the marginal benefit of that? What is the marginal utility of that? Versus what is the cost of doing that, right? What is the marginal cost? Okay, so what if you don't exactly know precisely whether it'll happen or not, right? So to 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 make sense of that, we are going to bring this in, right? We're gonna bring this into the model, and this is in utility theory dealing with this is called expected utility. Okay, so expected utility, it makes use of the mathematical concept of expected value in order to calculate a utility when there's some element of uncertainty. Okay, so let's just define what do we mean by uncertainty. Okay, so there's two different possible meanings of this. Okay, the first could be considered true uncertainty. All right, true uncertainty. True uncertainty just means we actually have no idea. What are the range of options that could happen. True uncertainty it is something like, what, I could, if I put my hand in this hole, you know, uh, what could happen? I don't know, right? Maybe I could grab hold of a bunch of treasure. That could happen, or maybe there's something down there that's going to bite me. I don't know, right? Maybe this is why we don't like to put our hands down into a deep hole that we have no idea what's in there, right? That involves true uncertainty, okay? Versus the what could be called probabilistic uncertainty. Probabilistic uncertainty is we have some idea. We don't know exactly what's going to happen, but we know based on what has occurred in the past, right? We say, look, usually we use the frequency approach to calculating a probability. We say, look, this happened 7 out of the last 10 times. We project that into the future. We say, all right, well, if the relative frequency here is 7 out of 10, we're going to consider that to be a 70% probability of this thing happening, or a 0.7. Okay, so now this is mostly what we're doing, right? Because see, true uncertainty is not measurable, right? That's the problem with it. Okay, remember utility theory and microeconomics. Microeconomics is a highly mathematical approach to economics. We try to measure everything, right? We're basically not comfortable with something that can't be measured, right? And that's one of the big difficulties with utility theory, right? Of course, not observable, not measurable. But again, we're trying to get around that, okay? So we are dealing with now probabilistic uncertainty. And if we don't know exactly what it is, then we're going to use this frequency approach. Or a lot of the examples that we're going to deal with are things like, if we flip a coin, we have here a random type of process, right? We say, what is the probability of some event occurring? Okay, so in terms of this, right, we're going to do a little bit of probability theory here. So our terminology, right, if we say like the probability of A, it's like this, right? Probability of A, okay? What this means is the probability of that event A occurs. Okay, so probability that event A occurs. And so then we would also have to say, all right, well, there's a probability that A does not occur, all right? And these two together, okay, just to keep it very simple, right? Let's say, look, there's only A can happen or it cannot happen, right? It either happens or not. There's no other option, okay? So the two of these together must always add up to 1, all right? So the probability of A is 0.3, then the probability of not A must be 0.7, okay, just for example. All right, so the way we're going to use this to calculate expected value or expected utility is very simple, okay? We are going to simply go like this, okay? The expected value, okay, of some event A, right? Expected value of A, all right? This equals the the value of that thing, whatever it is, okay? So the value of A times the probability that A occurs, okay? So, and then just to fill this out, we have to say, well, what else could happen, right? Okay, so what is the value of, let's say, not A? Multiply that times the probability of not A. All right. A lot of times in our examples, our problems or whatever, this second one is going to drop out because that's going to be 0. But just for completeness, okay, we have to multiply every option that there is. So there's 3 options or 4 options or whatever. We have to multiply the probability of each one times the value of each one. Okay, that's the basic rule of calculating expected value. Okay, so to give you a couple of examples. Okay, let's say, okay, let's say that you're going to flip a coin, and if it's heads, then you get $10, all right? And if it's tails, you get nothing, okay? Very simple, okay? Hey, I bet you this will come up heads. If you win $10, all right? Um, a lot of these involve gambling, because gambling, just in terms of the history of probability theory, the history of probability theory is developed by gamblers, right? The first treatises on probability were people who were playing cards and so forth. All right. So anyway, heads you get $10, tails you get $0. All right. So say, well, what's the probability of this, right? So probability of A in this case, 0.5, right? There's a 1 out of 2 chance. 1 out of 2 chance. Get it? That when you flip a coin, it's going to come up heads, all right? And then the probability of not A, okay, tails, is also 0.5, okay? 1/2. All right, so we're going to put this into our formula, and we'd say, well, what's the expected value here of A? Well, we're going to go 0.5, okay, that's the probability, times the value that we get here, okay, plus not A, okay, the probability 0.5 times the value 0, okay, so this one is going to, the second term there drops out because it's 0.5 times 0. Anything times 0, of course, is 0. All right, so we're left with 0.5 times 10, which gives us 5. All right, so the way we would interpret this is we would say, look, the expected value, this is also the same as saying the average, okay, in situations that involve probability, where we're not exactly sure what the outcome is going to be, but we have some idea based on the past or based on whatever kind of, if it's a well understood kind of random process like this, then we can say, okay, the expected value of a situation like this, where heads gets you $10 and tails gets you $0, on average, that is going to be $5. Okay, so this is going to be the average or the expected value of this situation. And if we put utility in terms of money, we would say, okay, the expected utility of this situation is $5. All right. Strictly speaking, we can't measure utility in dollars, but anyway, we're going to do that anyway, right? We have a way to work around this. This is what our indifference curve framework was trying to show. All right. So now look at this, right? You can't actually get $5. $5 is not an outcome that's possible here, right? You can get either $10 or $0. Those are the outcomes. But $5 is still the average, right? Because half the time you're going to get 10, half the time you're going to get 0, right? Over the long haul, you would expect this to be worth $5 per attempt, all right? That is the expected value or the expected utility. So this works equally well for losses, okay? So let's imagine, take another example. Let's say that you have a 5% chance of losing $100, all right? 5% chance of losing $100, okay? So all we're going to do here is add a negative sign, all right? So the expected value of this situation, we'll just continue to call it A, okay, event A. Well, you have a 5% chance, okay, that's a 0.05 times, now this is the value, okay, if you're losing $100, the value of that is negative 100, okay? So 0.05 times a negative 100, all right? And then the other thing that could happen, of course, is that you don't lose the $100, right? So you don't lose, and that has a 0.95 probability. Remember, the thing plus the not the thing, right? Whatever it is, A, probability of A plus the probability of not A, that always has to add up to 1, right? So now, what happens if you don't lose $100? Well, it's 0, okay? What's the value of that? Nothing. It's the same as what's happening now, all right? So this second term, again, that just drops out, okay? So we left with 0.05 times negative 100, and what this gives us is negative 5, all right? And this is in dollars, okay? So what does this tell us? Well, it tells us that on average, this 5% chance of losing $100, we should value that at negative $5, all right? Negative $5. That's the expected. So we can make sense of both uncertain gains and uncertain losses by using expected value. Another aspect of this that we can talk about is called the reversion to the mean. Okay, so reversion to the mean, or simply mean reversion. Okay, so in mathematics and probability theory, mean and average and expected value, these all are used interchangeably, okay, because the average or the mean involving probability is just called expected value. And, in practice, everyone uses these terms interchangeably, okay? Imagine that we are playing a game, okay? Here's the game. And the game is you're going to roll a 6-sided die, and you are going to win the amount of money that is showing on the face of the die, okay? So you're going to either win $1 if you roll a 1, or you're going to win $2 or $3 or $4 or $5 or $6, depending on what is showing on the die, all right? So, okay, I hope that's understandable, right? So what is the expected value of this situation, right? What happens here on average, right? So the expected value of this situation, all right, expected value, let's just call this game, we'll call it A, right? So what happens? Well, 1/6 of the time, okay, the probability, because we assume each one of these things is equally likely, right? It's a fair 6-sided die, all right? So each one has an equal probability of happening. There are 6 things that can happen, okay? So the probability of each one is 1/6, okay? So you've got a 1/6 probability of winning $1. You've got a 1/6 probability of winning $2, and so forth. So if we collect all these terms, right, we're going to end up with 21/6, which gives us 3.5. All right. So what is this saying, right? Well, this is saying that the expected value of this situation is $3.50. Okay, so expected value, like when we the word value, right? It's in terms of money, right? So we the unit on there is dollars, right? So we have to put everything in terms into a value framework, and the probability is just a number between 0 and 1, right? The probability thing doesn't have units, but this part does. Okay, this part is in dollars. All right, so expected value of this situation is $3.50. This is the average or the mean or the expected value in this situation. All right. So let's say that we observed a mean that was different from this, right? Let's say that just, for the hell of it, right? We say, all right, we're going to roll the die and see what happens, okay? And let's say that this is what happens, okay? You get a 1, and then you get a 2, you get a 3, you get another 2, you get a 1, okay? So you've done this 5 times, and you could say, all right, well, what is the average that I've gotten here? Okay, so the average, well, we're going to add these numbers up. Okay, so the average, we could call this the individual average, right? So the individual average, that means of these 5 throws that you just did, well, we're going to take, okay, 1, add it to 2, add it to 3, plus 2 plus 1 like this, and we're going to divide by the number of throws. Okay, so uh, add up the results of each throw and then divide by the number of throws of the dice. All right, when we do this, we get, what's this equal to? 8, I'm sorry, this is 6, the whole thing is 8. Okay, so we get 8 over 5, and this is equal to 1.6. All right, so here's the thing that we observe about this, right? The individual average, here's the situation, okay? The individual average is far below the expected value, right? The expected value, 350, our individual average here, 1.6 or 160, okay? So now we have now we have something that we could actually predict, right? So what could we do with this information, right? Well, we have an individual average which is far below what we expect the long-term average to be. So in other words, what do we expect will happen? Like if we're going to roll the die 1,000 times, right? And this is what's happened so far, right? Our first 5 throws have had this average. What we expect to happen over time, well, let's say we're going to throw it a 6th time, a 7th time, an 8th time, etc., right? And we're going to calculate the average based on what's happened so far, but we're going to add to that every time, right? Every throw, like let's say the next throw we get a 5, okay, we're going to add that to the top, and then we're going to divide by the number of throws again, which would be 6 now, right? So what is going to happen in this situation is that the individual average is going to revert to the mean, right? The individual average is going to rise until it is close to or equal to the expected value, right? Because it's just mathematically improbable that you roll more 1s and 2s and 3s. That's what it would take in order to keep the average below 3.5, right? It's improbable that you would throw more of those than you throw 4s, 5s, and 6s over time, right? What's going to happen is this is going to revert to the mean, okay? Just like if the individual average, let's say the individual average had been 420, right? The expected value of the situation remains 350. What do we expect to happen? We expect to revert to the mean. That means the individual average is going to fall to the overall expected value, okay? We see this all over the place, right? We can see this in terms of the stock market, right? We can look at an individual investor's returns, right? That's the individual average relative to the market's returns. And we see this same principle occurring, right? That is, individuals who are their performance is far better than the market, what happens over time? They tend to revert to the mean, right? Those that are below also tend to revert to the mean over time. Okay, so many things we see this in, right? A reversion to the mean, or these rock solid statistical principles that we observe everywhere. Okay, so I give you guys a couple of different problems here. Um, so to say like, well, which would you prefer in this situation? All right, so using the concept of expected value, which would you prefer? All right, let's say we would divide it into two sides. Okay, would you prefer A? And let's say A is $500. All right, or would you prefer B? And B is uh, an 80% chance of winning $1,000. Right? So which would you prefer? Uh, $500 is certain, right? So if we say what's the expected value of this, well, the expected value of this, the probability is 1. The the value of it is $500, so very simple, right? The expected value of that situation is $500. Well, and what do we make of B, right? Well, B is we have to calculate the expected value of this. We have to now take the probability, zero point 0.8, multiply it times the value, 1,000. Now we haven't said this, but the it's kind of unsaid here, but if you don't get this right, if you don't win the $1,000, then you get nothing. Okay, so the zero point 0.2 probability here is 0. All right. So, but again, this part drops out. Right. So, and we're left with zero point 0.8 times 1,000 is $800. Okay, so microeconomic theory would predict. Okay, microeconomic theory would predict that a rational individual, right, a rational person, which we've assumed that everybody is, right? Homo economicus. We've said that that's the essence of being human. That's what human nature is. It's being rational. It's maximizing utility subject to the constraints. So that if somebody said, look, you can have either A or B, but you can't have both, well, the person, any rational person, is going to prefer B to A, right? Because the expected value is higher, right? So we're just kind of expanding on this, right? Remember, we've said, look, here's what people do. They maximize utility subject to the constraints, okay? And all we've done is we've just added a little tiny bit onto this and said, it could be expected utility, right? This is what's going to happen on average, right? Now, here's the thing, right? If there's probability, it means that some of the time, you're going to walk away with nothing, right? Like you could choose B, and yeah, you do have an 8 out of 10 chance of winning $1,000, but you also have a zero point 0.2 chance, 20% chance of winning 0, right? Now, the microeconomic theory says, look, that's no different than where you were right now, right? Like you didn't win $1,000. Well, okay, but you had a zero point 0.8 chance of winning $1,000. What's your chance of winning $1,000 without that, right? Yeah, you might walk out away with nothing 20% of the time, but that's a lot better than your normal state, right? In which you don't normally have an 80% chance of winning $1,000, right? So this is the thing, right? But this kind of choice often presents people with a lot of conflict, right? That's the observation. When we actually ask people which would you prefer, we often find that people prefer A, right? People prefer A. Okay, so microeconomic theory has a way of trying to make sense of this, okay? And this is called being risk averse. Okay, being risk averse means, well, you are opposed, you don't like the idea of taking a risk, and so you'd be willing to pay something just to avoid that, right? You're paying to avoid, right? So what is that? Well, you're accepting something which is less good, right? 500. This is if you decide you prefer A, it's kind of like you're paying $300 to explicitly to avoid this situation right here, right? That you would walk away with nothing. Okay. Now, why is that? Well, that's what risk averse means, right? So it would pay to avoid a risk. Okay. That's risk averse. Now, some people are willing to accept the risk. Okay. So they are risk neutral. Okay. They don't fear the risk, right? And that's kind of like where we are with again, microeconomic theory. What it predicts is, a rational person. They don't have any particular attitude toward risk, right? They are neutral with respect to risk, okay? But, microeconomic theory, right? It's all about different preferences. And, okay, some people might have this, right? They don't like risk. And some people might like it, right? They might be risk seeking, okay? And what does that mean? That means if a risk is available, you'll take it, right? Absolutely, yeah. You might even take it if it were, you might even pay to take a risk, right? So, this is like the thrill seekers um, of the world, right? Like you just jumped out of a plane, or you went down this like super steep course on a mountain bike. Don't you know you get hurt? Yeah, but that's exciting. I feel alive. Um, so that's risk seeking, right? And there's a lot of risk seekers out there. There's a lot of risk averse people out there too, right? We are just observing people's behavior. We can see some people will take a risk; they'll even pay for it, all right? So risk averse, risk neutral, risk seeking, all right? Yeah, just different preferences, right? So by the way, where this comes in, expected value, we can use this to explain things like insurance. So remember this situation, right, where he said, "Hey, what is this? You had 5% chance of losing $100. Uh, Imagine that you could uh, pay to avoid a loss, right? That's essentially what insurance is, right? So let's say you get home insurance, that protects you against certain natural disasters, or whatever it is, right? Whatever is covered under your home insurance policy, right? Saying like, okay, look, there's a very small chance that something catastrophically bad will happen to your house, right? Let's say there's a 1% chance, on any given, you know, that's probably way too high, right? Let's say it's a 0.01% chance that your house gets completely and totally destroyed, right? Um, so, and let's say that involves a loss of $250,000. Okay, so $250,000. Wow, 0.01% chance of that, right? Okay, well, what is the expected value of this thing, right? Well, again, we're going to take the probability. Okay, so 0.01, we gotta put two more zeros in front of it, right? Times this negative 250,000, right? Okay, this equals $25, right? So you might be willing to pay something for this just to avoid the chance, right? To sleep better at night, right? We'd say, all right, well, the expected value of this, it's a negative, right? The expected value of this negative $25, if you are risk neutral, this means you would pay $25. Let's say this is per year or whatever, right? So you pay $25 per year just to avoid this situation, all right? So home insurance, or maybe it's life insurance, whatever it is, right? This explains why a person might like to do insurance, all right? And since we've mentioned insurance, there is another related concept which comes up here, which is called moral hazard. All right, moral hazard. Moral hazard means, look, if you are protected from risk, if you're protected from risk, you might change your behavior, okay? You may change your behavior. You may, in fact, become, you might take on more risk, right? So, are you going to be as careful? If you know your car is covered by insurance, maybe you'll drive a little bit faster. Maybe you won't be as concerned about getting into an accident because you know it's not as catastrophic, it's not as bad. Well, I mean, of course, somebody could get killed, right? But you're protected from the economic consequences of that, to some extent, right? So that's what moral hazard is, right? Our behavior may change as a result of being protected from risk or not. Okay, so researchers did experiments and surveys in which they tried to figure out, they tried to pin down, like we have this question: are people risk averse? Are they risk neutral? Are they neutral? Are they risk seeking? Now remember, microeconomic theory is setting this up and saying, okay, look, you can have a different preference. Some people can be risk averse, some people can be risk seeking, but the one thing that we absolutely must insist on, right? The one thing that is part of the theory is that everyone is consistent, right? You might recall from the previous lecture on utility theory that this is the transitivity principle. Okay, so we expect people to be consistent, meaning their preferences are transitive. If they are risk averse, they are going to have the same degree of risk aversion throughout all their choices. That's just a part of them, right? That's like, hey, if you don't like peanut butter, you're not going to like it in sandwiches, you're not going to like it in sauces, you're not going to like it anywhere. You don't like peanut butter, right? You're not going to like it some places and not others or whatever. That would violate the transitivity, right? That would be inconsistent. Okay, so the same thing about your attitude toward risk, that is going to be totally consistent throughout everything that you do. Okay, so let's say we had a couple of different options, right? Here's the thing: the experiments and the surveys, what they noticed, what their results showed. Okay, the results showed that people are not very consistent at all when it comes to risk. Okay, they're not consistent, and that became a difficult thing to explain, right? So let me give you an example of what I mean by that they're not consistent. Okay, so let's imagine that you could have either A over here, right, or B. Okay, two different options, and let's say that A involved a 95% chance to win $10,000. Right? 95% chance to win $10,000. And we know that the expected value of this, okay, 0.95 times that 10,000, this is equal to $9,500. Right? Again, that's not an outcome that can happen. There's two outcomes here, 10,000 and 0. But on average, right, this is worth $9,500 and $9,500. Okay, so, and let's say that B is a 100% chance of winning $9,499, right? And we can see, look, this is anything that has a 100% chance. Anything that has a 100% chance is a 1 times that, right? So we are comparing, right, $9,499 is the expected value here to $9,500, okay? So, and again, microeconomic theory would predict that if a person is risk neutral, they're always going to prefer A to this situation, okay? Now, what we find is, when we ask people, many people, right? In fact, like it's very, very common, right? People often, they want B, right? B is a sure thing. Okay, yes, you accept a lesser amount, but you have 100% chance of that, right? Now, just to extend this, right, with our logic, okay, this implies that you are risk averse, okay? So if B is preferred to A, right, that's what it means. The person must be risk averse, right? However, okay, if you're risk averse, that has to apply to all situations, right? What if we were to flip this situation and bring it into losses, right? And say, all right, well, what happens if it's like this, right? A 95% chance to not win, but to lose $10,000, right? Versus, let's say, B is a 100% chance to lose $9,499, right? So, okay, again, we could calculate the expected value, right? The expected value here is negative $9,500. The expected value here, negative 9499, right? So, again, if you were risk neutral, we're saying, look, you should choose B here, right? You're risk neutral, you choose the one that has a smaller negative number, right? So, okay, here's the thing, right? If now, if A is preferred to B in this situation, it means that the person is now risk seeking, okay? So that's fine, right? It's just that where it causes a problem is what the results of many repeated experiments show is that people flip back and forth between these, right? The same person who would prefer this, right? They'd much rather have the 100% chance of winning, the $9,499, which would signal that that person is risk averse. Well, then it comes to you ask them about, well, how do you feel about, would you rather have the 95% chance of losing $10,000 or would you rather have the 100% chance of losing $9,499? Now, again, from the perspective of microeconomic theory, these things are identical, right? So the person who is risk averse, the person who is risk, but what we often find is this person is quite willing to take a risk when it comes to this, right? When it comes to losses. So people will often choose uh, people will often choose A in this situation, right? So going from A to B, reversing that, right? This shows, okay, that the person is not being consistent, right? They are risk averse when it comes to gains, and risk seeking when it comes to losses. That's very inconsistent, right? We also find that this changes when it depends on whether the probabilities are large or small. Okay, so this is a large probability, right? The 95% is it's high. It's close to 1, right? 0.95. What if we reverse this and said, okay, look, A is a 5% chance. It's a 5% chance of winning $10,000. Or you got a 100% chance of winning $501, right? 5% chance, so 5% chance of winning $10,000, or 100% chance of winning $501. All right. So again, if you prefer A here, right? If you prefer A, it indicates that you're risk seeking. Okay, so A preferred to B, again, risk seeking. Why is that? Well, because the expected value here, 0.05 times 10,000, right? 0.05 times 10,000 is $500. Okay. So if you're willing to take a flyer on that, right, versus the sure thing actually has a higher expected value, right? It's like you're saying, look, I'm willing to pay $1 essentially, right? Because this has a $1 lower expected value. I'm willing to give up $1 in terms of expected value to have some upside potential, right? Because what you've given away here, if you choose B, the 100% chance of winning $501, there's no upside potential, right? There's no downside potential either. Okay, you just have $501. There you go, right? Now this, oh hey, you got upside potential, right? You could win $10,000. But what's going to happen most of the time? What's going to happen most of the time is you're going to walk away with nothing, right? because that's the other thing that can happen, right? You got a 0.95 of 0, okay? So if the person chooses this way, right, they're risk seeking. Um, or we could flip it around and look at it from the perspective of losses, right? We could say, what about apply that save percent chance to a loss, right? A negative $10,000, right? Or you could just take the loss right away, right? The 100% chance uh, that you lose $501. Okay? So, again, what we see here is the person flipping from being risk seeking to risk averse, right? And this was a thing that economists had to try to explain. And some economists who looked at this early on were named Kahneman and Tversky. Right, Daniel Kahneman, Amos Tversky, and they created a theory here called prospect theory. And prospect theory was designed to explain some of these findings. So how do people, people are not behaving the way that we expect them to behave with expected value or expected utility. They don't seem to be maximizing their expected utility in the way that the theory predicts. Okay, so the people want some of the findings from prospect theory is that people overweight and underweight certain probabilities. Okay, they don't they don't behave consistently with respect to the probability. They treat gains and losses differently, right? So we're trying to explain. I have to say, prospect theory doesn't exactly explain why people do this, but it offers a kind of a framework, right? It basically says there's loss aversion. People are they look at it relative to what they could gain or lose. Um, all right, so um, this is an aspect of a emerging part of microeconomic theory. This is behavioral economics. Okay, behavioral economics started out. It was first called experimental economics, uh, and it kind of morphed and changed over time. Right. So also related to game theory. I have a separate video on this that I'll get into in a little more detail. All right, that's my lecture for today. Thank you very much.